Our first speaker of this session will be Professor Giovanni Paolini from University of Bologna. He will tell us about the K-pi1 conjecture for affine Artin groups. Let's welcome.
Thank you. Good afternoon. In the first part of today's talk, I will introduce what this problem is about, the K-pi1 conjecture. And then I will tell you a little bit about the story of our proof in the affine case done with Mario Salvetti. Okay, so let's get started. The first character in this story is reflection groups. And the way I will introduce them is as discrete groups of isometries generated by orthogonal reflections in some Euclidean space R to the n. And every time you have a reflection group, the natural geometric object associated to it is the collection of all reflection hyperplanes for all reflections in the group. So in the pictures, you see basically the two cases that can occur according to my definition. On the left, you have the arrangements of hyperplanes associated with finite reflection groups. So you get a collection of hyperplanes, in this case, just lines in R2, all passing through a common point, and the reflection group is finite. I will also call finite Coxeter groups, finite reflection groups spherical, because if you draw a unit sphere centered at the intersection point, and you restrict to this sphere, you see an arrangement of subspheres, and you can restrict the group to a reflection group of isometries on the sphere. The other case that can occur is that you get an infinite group. In this case, you have infinitely many reflection hyperplanes. They do not all pass through a single point. You truly get affine isometries of the Euclidean space, and this is why we call this case affine. Okay. The most fundamental example is the symmetric group, which is a spherical reflection group. You can see it by thinking about the transposition ij as the reflection with respect to the hyperplane xi equals xj. Here is the picture. Now, this is the symmetric group sigma 3, permuting a 3-element set. There is the small subtlety. This happens for the symmetry group that we would think about the symmetry group as permuting the coordinates in Rn, but all these transpositions fix the line spanned by 1, 1, 1, 1, 1. So we can actually restrict to the orthogonal to this line. So this is why we see a 2-dimensional picture, not a 3-dimensional picture. And here are the 3 reflection hyperplanes associated in this case with the 3 transpositions. Reflection groups are a special instance of a more general class of interesting groups called the Coxeter groups, already introduced at several points during this conference. A Coxeter group is a group with a finite set of generators S, and they all square to 1. And for each pair of them, we are allowed to choose a relation between those 2 generators. The relation has a given length, MST, which we are free to choose. And the relation is that the alternating product of the 2 generators is the same whether you start with one or with the other, provided that the words have this length that we have chosen, MST. MST is at least 2. It is allowed to be infinity, which means that there is no relation between S and T. Reflection groups are a particular instance of Coxeter groups. We can see it in the example here. If you have your reflection group, you can fix any of the chambers These are the connected components of the complement of the arrangement. So let's say we fix the chamber down here. We use the walls with respect to the chamber as the generators of the group. Let's call them A and B. And the dihedral angle between those two hyperplanes will tell us exactly the length of the relation that we see in the presentation as a Coxeter group. For example, if those two walls are orthogonal, we get a commuting relation between the two reflections. If you see an angle of pi over 3, like in the picture here, you see the braid relation ABA equals BAB. Okay. The other important family of groups that we are going to meet today is Artin groups. We can introduce Artin groups by taking the presentation of a Coxeter group and removing the relations that S squared should be equal to 1. So for each Coxeter group with its Coxeter presentation, we get an Artin group. If W is a Coxeter group, I indicate with GW the corresponding Artin group. The braid group is the Artin group associated with the symmetric group. And there are other interesting examples. Free groups and pre-abelian groups are Artin groups. Another well-studied family is that of right-angled Artin groups, in which all relations are either length 2 or they don't exist, length infinity. Now, earlier in this conference, people more important than me, claimed that defining objects by generators and relations is not optimal. And fortunately, for Artin groups, we can see them in another way, more topological. They arise as the fundamental group of a certain topological space. So the space is constructed as follows. I will cheat a little bit. I will tell you the definition, the construction in the case of reflection groups, but this can be done for arbitrary Coxeter groups W. So let's assume that W is a reflection group in R to the n. We take our arrangement of hyperplanes. We go to Cn, and we remove from Cn the union of all these hyperplanes complexified. So same equations as in the real case, but over the complex numbers. And we also take the quotient by the action of the Coxeter group. Let's make an example because this is a little bit easier than what it may look. Let's take the symmetric group, sigma 3, as before. What happens if we spell out this definition? We are in C3, so triples of complex numbers, x1, x2, x3. We remove the reflection hyperplanes, which are defined by the equation xi equals xj. Okay, so now we have removed them, and we are asking that these three complex numbers are pairwise distinct. And we take the quotient by the action of the symmetric group, which permutes these three complex numbers. So we get the space of configurations of three unordered points. So we don't need to remember which is the first, which is the second, which is the third. Okay, and now we take the fundamental group of this space. So we started our favorite configuration of 3 points, and a path in this configuration space forms a braid. You move this configuration through time. These 3 points must never collide at any given time, and you must end up in the same configuration. The points can swap with each other. That's fine. Okay, and this is what gives the name braid group to the Artin groups that come from the symmetric group. Okay, yes? Sorry, say it again. Oh, I see. So you mean if I change? So we do this for a specific representation of the Coxeter group. There is a little bit of freedom, like here for the symmetric group, we can do it for either in C2 or in C3, and we get to the same space up to homotopy equivalence. So if you do it reasonably, then you get the same thing. Okay, and the K-pi1 conjecture states that this configuration space, YW, is always a K-pi1, or a classifying space for the discrete group GW, the Artin group. This is a problem that goes back to more than 50 years ago. It originates from algebraic geometry, but it has ramifications in other areas. It is interesting for people who study Artin groups, for example. I will mention a little bit about this in a moment. But before going there, let's see very, very shortly some of the history of this problem. The most important development was the proof in the spherical case by Deligne in 1972. This came shortly after, or around the same time, of a proof by Briscorn of some special cases within spherical Artin groups. And after that point, some other cases were addressed, but perhaps crucially, the affine case was never sort of fully addressed. Only some affine families were addressed. And well, the story of today is that we completed the full proof of the affine case with Mario. So this completes the picture for all Coxeter groups that come from reflection groups, that are reflection groups in the way that I define them to you. This is not the full problem. One could argue that most Coxeter groups are not reflection groups in the way I define them. So we get, for example, Coxeter groups that act as reflection groups in the hyperbolic space, and more situations. I am skipping some of the history, but I'm just trying to be brief. Now, from the point of view of someone who is interested in braid groups and Artin groups, this is a central problem among many other open problems. In fact, very little is known about Artin groups in general. We don't know if they are torsion-free. We don't know their center. We don't know how to solve the word problem. And the K-pi1 conjecture actually implies torsion-freeness, implies the knowledge of the center. It also allows one to compute the homology and cohomology explicitly, and this has been a large line of research since computations on the braid group. Another interesting perspective to look at this problem is from the study of arrangements of hyperplanes, or hypertori or hypersurfaces. Here, there is a more general problem of trying to classify when the complement of an arrangement, say in C to the n, for example, is a K-pi1. For instance, there are some particular cases where this is conjectured to have an affirmative answer, we happen to have a handwritten note by Deligne explicitly stating the second of these conjectures. That is, if you take an arrangement in Rn, which is simplicial, so all the chambers are simplices, then its complexification is conjectured to be k-pi1. So this would be a generalization of the theorem that we proved, essentially. Okay, so now I will have two slides that are a little bit more technical. I want to give you a little bit of the ideas behind the proof, and then I will tell you a little bit about the story of what we did. So bear with me, some small technicalities. It is useful. So it has been useful for us to think very much in combinatorial terms. So I am telling you very shortly the basics of what is now called the Garside theory, which is a way to reinterpret what Deligne did to prove the k-pi1 conjecture in the spherical case. Okay, so let G be a group, could be a Coxeter group, for example. R a set of generators, which is closed under taking the inverse. And you fix a special element, small g, in your group. Okay, now you construct the interval from the identity to your special element g in the Cayley graph of your group with respect to the generators that you have chosen. Okay, so this is an interval. It's a partially ordered set, or a poset, in a natural way. In a Cayley graph, the edges are labeled by generators. Okay, so this is a poset with labeled cover relations. From this interval with labels, we can construct another group, which is called interval group, which is the group generated by the labels in your interval, subject to the relations that you see in the interval. So let's make an example. So this is, again, the example of sigma 3. It is stated more generally for finite Coxeter groups because this construction works for all Coxeter groups. Okay, so G is a finite Coxeter group, for instance, sigma 3. R is the usual generating set as before. And the special element is the longest element of your Coxeter group. So this always exists for finite Coxeter groups. In sigma 3, it's it sends 1, 2, 3 in 3, 2, 1. Completely reverses your word. Okay, so you can build the Cayley graph of the symmetric group. So it's written here. I'm calling delta the longest element. So in this case, it's ABA or BAB, where A and B are the transpositions 1, 2, and 2, 3. Now, from this poset, from this interval, we actually care about the labels on the edges. We don't care that much about what's on the vertices. So the important information here is that the edges are labeled ABA on the left and BAB on the right. Now, in the symmetric group, A is the transposition 1, 2, and B is the transposition 2, 3. But now we forget about this, and we treat A and B as abstract generators. Okay, and we can construct the interval group, which is generated by A and B, subject to the only relation that we see in this interval. In this interval, if we go left from bottom to top, we read ABA. If we go right, we read BAB, and we set those two words as being equal. Okay. Okay, so this is a construction that works in general to build spherical Artin group from its finite Coxeter group. So if you wish, it's a third way to build an Artin group, a spherical Artin group. Okay, why is this useful? And this goes back to work by Garside on the word and conjugacy problem on the braid group. Then the theory was developed quite a bit. I'm condensing some things in a single slide. The core is that if you have some combinatorial hypothesis on your interval, and these properties are a balanced lattice, then you get some information about the interval group. You get a nice normal form, so you can solve the word problem, and more importantly for us, you get an explicit construction of a k-pi1 from the poset. So without going too much into details, but you take your interval, you build the order complex, which is a simplified complex, and you quotient it by gluing together things that are labeled in the same way, more or less. Okay, so you get a very explicit CW complex. If you know combinatorially your interval, then you know the CW complex. Okay, and under these two combinatorial assumptions, you get that this is a k-pi1. Excellent. So in our case, balanced is always going to be easily true. The lattice property is the crucial one that will come into play. Lattice means that any two elements in our poset or interval, they have a least upper bound and a greatest lower bound. Okay. And the interesting thing is that spherical Artin groups, so the example that I made earlier is a Garside structure. So if you take a finite Coxeter group, the longest element, you build the interval, that interval satisfies these combinatorial properties. And so this makes spherical Artin groups Garside groups. So they have all these nice properties. They have an explicit k-pi1 classifying space, and in some sense, this k-pi1 is very related to the Linus proof of the k-pi1 conjecture in the spherical case. Now, a little bit more recently, around 2000, year 2000, it was discovered that there is a very different alternative way to realize spherical Artin groups as Garside groups. And this other way works as follows. You are still in your finite Coxeter group. You, instead of using only the standard generators, you use all reflections as generators. So if you are in the symmetric group sigma 3, you are using all three transpositions instead of just two. Okay, we call them A, B, and C. And as a special element, you pick an element called the Coxeter element, which for the symmetric group is just an n cycle. Okay, so you can think that if you are in sigma 3, you have your three transpositions, and on the top you have the 3 cycle 1, 2, 3. And the 3 cycle, you can write it as 1, 2 times 2, 3, or 2, 3 times 1, 3, or 1, 3 times 1, 2. Okay, this is the poset that you get. This is a balanced lattice and gives rise to a Garside structure for spherical Artin groups. So very nice things happening, and let me stress that these two sides of this slide, they talk about very different combinatorics. So on the left side, we have what is also called the weak order on Coxeter groups. Okay. For example, this is sigma 3. We are used to it now. This hexagon. This is the picture for sigma 4. This is the interval. Okay, we care a lot about the interval. It's the one skeleton of a polytope called permutahedron. On the right-hand side of the previous slide, we get a very different combinatorics. It's the combinatorics of non-crossing partitions. Okay, so basically, okay, on the left, this is the Cayley graph of sigma 3 with respect to the 3 transpositions. This is the special element that we picked. So the interval, we throw away the stuff on the right. The interval is over here. And this is what happens in sigma 4. Let me zoom in sigma 4, because actually you can show that this is the same as the poset of all so-called non-crossing partitions of a square, in this case, a polygon with n vertices in general. So it's this is a poset, a lattice, very well studied. It fits in Catalan combinatorics. Catalan numbers have also been mentioned in this conference. So yeah, two very different combinatorics. They give very different ways to work with spherical Artin groups. Okay, so let's make our first step outside of the world of spherical Artin groups. What happens if you move to the affine case? Now, the standard Garside structure, the one on the left, does not exist for infinite Coxeter groups, because there is no special element that you can pick. There is no longest element, and you cannot make this construction. On the other hand, I'll go back just just maybe over here. You can do this construction in an infinite Coxeter group, because you always have these Coxeter elements to choose from. What happens is that you get an infinitely wide interval, but if you are willing to accept this small technical issue, then it could be possible to go forward. So it was interesting to see, can we advance using this so-called dual combinatorics, the combinatorics of non-crossing partitions for infinite Coxeter groups. Unfortunately, it was shown by John McCammond that in the affine case, this non-crossing partition poset is not always a lattice. He explicitly classified in which cases it is, in which cases it is not. So, but this seemed to be like a major obstacle to doing anything along this path. Well, not completely, because John McCammon and Robert Salway were able to still get something out of this dual structure. Well, quite a bit actually. They showed that the interval group from this dual structure is still the Artin group. So this seemingly crazy construction with the interval group using the dual combinatorics, it does give you the correct group. In general, this is a conjecture, so this is why there is a dual word here. So in general, you call dual Artin group the interval group that arises from the dual structure. We don't know if it's the same or not as the standard Artin group. And they were also able to embed this into a larger Garside group. So they got the word problem and torsion freeness like inherited by a larger Garside group, but not enough to approach the k-pi1 conjecture. So this is more or less the state of things when we started working on this problem from the perspective of the this dual structure. This was during my PhD. We had some previous unsuccessful attempts. At some point during my PhD, I met a professor at a conference. He asked me, "What are you working on?" I replied, the k-pi1 conjecture. And he told me, "Well, you should change problem." Okay. But I mean, it was a very reasonable suggestion, and I did work on other problems. And in fact, it was only until near the end of my PhD, I was already writing my thesis, that we had the first serious advancement, let's say. We had this very fruitful meeting where we realized what then became the first step in the proof. So we realized that there was a great hope that even without the lattice property, the same construction of a k-pi1 could give a k-pi1 still. Not for a general interval in a general group. I'm talking specifically about the dual structure for affine Coxeter groups. So in fact, this first step ended up not being the most difficult part to prove, but it was definitely the most surprising one. Because if you read this theory of Garside groups, the lattice property is extremely crucial everywhere. So it is used to compute greatest common divisors, least common multiples. In the proof that CW complex is a k-pi1, you use it a lot to build the universal cover explicitly. To get that intersection of parts still behave well. The lattice property is crucial. So this was the point where we really started to see something. The next step was, I think, reasonably natural. So we had a k-pi1 for the correct group. We wanted to relate it with our configuration space. Okay, remember, YW is the configuration space that we care about. We had this k-pi1, kw. To relate these two spaces, we constructed a CW complex with the same homotopy type as the configuration space sitting inside our k-pi1. So a fairly reasonable thing to do. This was also not the most complicated part of the proof. I should also mention at this point that there is a very famous CW model for the configuration space of an Artin group. It is called the Salvetti complex because Mario developed it a couple of decades ago. It is actually, it works more generally for complements of hyperplane arrangements in CN if the hyperplanes have real equations. So this is actually the reason for the prime here. This is because XW is reserved for the Salvetti complex. If Mario were giving this lecture, he would probably skip over the part that is called the Salvetti complex. So it's good that I'm giving the lecture. This complex here is related to the classical Salvetti complex in the sense that if you look at it from afar, it has the global combinatorics of the Salvetti complex, but if you zoom in, it has the dual combinatorics of this k-pi1. Okay, so now, basically, it really felt like there was only combinatorics of Coxeter groups in our way to finishing this. Okay, to finish the proof, we would need to show that these two spaces are homotopy equivalent. So, for instance, building a deformation retraction from our K-pi1 to the subcomplex. I made some numerical computations, and this turned out to be true up to arrangements in dimension 5, in R5, so up to rank 6. So it was very promising, and it really seemed that there was a lot of room for constructing this deformation retraction, like making random collapses more or less was working. So lots of room, but still not clear how to do it in general. There was also this other small issue that, well, I was finishing my PhD. So, well, I added a last chapter to my thesis with these partial results and the numerical computations up to dimension 5. And then, fortunately, I had, so I had at that point already accepted a position in industry, but I had 6 months of a postdoc with Emanuele De Lucchi in Switzerland, in Fribourg. So I had these 6 months to continue working on this problem. So basically, for this, for a couple of months, I was there in Fribourg. I had almost zero social life. About once a month, I would go back to Pisa to work with Mario and to see my wife, who was still in Pisa. And we made reasonably steady progress with a couple of bumps, positive bumps. And basically, we were able to develop enough of understanding of the combinatorics of this dual structure to build this deformation retraction. So this is the third and final step. It was by far the longest one. One of the bumps was in realizing that it was useful to pass through proving that this interval is shellable. So for those of you who know a little bit about combinatorics of posets, shellability is a nice property that comes useful in several occasions. Shellability was proved for the dual structure associated with finite Coxeter groups. So it was probably interesting by itself to have it extended to affine Coxeter groups. And so a couple of months into my postdoc, we finished the proof and we wrote it up, and it was I think like we put it on archive 2 weeks before the end of my postdoc, so the timing was pretty good. So the theorem that we got is well, the K-pi1 conjecture for affine Artin groups, and in fact we also got partially independent proof that the dual Artin group is the same as the standard Artin group in the affine case. This is a pictorial diagram for the same proof as the one I described. So what would be the idea? You have your Coxeter group, you build your dual combinatorics, your poset of non-crossing partitions. From this, if you just look at the labels on the edges, you can construct what is called a dual Artin group. And Garside theory would suggest this candidate k-pi1 CW complex. Okay, but if you don't have the lattice property, this is not for free. You don't know if it's a k-pi1, but step one was to believe that it was, and that ended up being true. And then what remains is to relate it with our configuration space. A nice feature. And this puts together well a ton of combinatorics, also geometry, topology, obviously, and group theory when you work with the presentation of this dual Artin group. A nice feature of this approach is that it is not there isn't an obvious reason why it shouldn't be done more generally. So the natural question, which we started working on, was can we generalize this further? This is very much still work in progress. The most interesting result, which is a positive result that we got, is that you can indeed extend this overall approach to the case of rank 3 Coxeter groups. So these are Coxeter groups with 3 generators, and most of them are of hyperbolic type. Like, this is the arrangement of a typical rank 3 Coxeter group. And in rank 3, things work in the best possible way, in the sense that you also get the lattice property. So proving that complex is a k-pi1 is actually easy because you get the lattice property, and well, everything works essentially. We have been attempting to extend this. We got some negative results in the sense that the way we were hoping to prove shellability does not seem to extend as easily as we were hoping. But so far, the negative results are not about the whole thing, but just smaller steps. So we are still hoping that the whole thing actually can be done. Okay, so maybe I want to take this chance to thank my wife, Alexandra, who has always been supporting me through my career. Thanks to Mario, always. And thank you for listening.
Thanks, Giovanni, for the very interesting talk. Are there any questions? So you said, okay, that was very loud. Okay, so you said you don't have a lattice structure there, but despite the lattice structure, you still can show that it's
Yep.
So is there some kind of weaker structure than lattice that allows you to do that?
Unfortunately, no, that we know of. What we did was very specific to like knowing this this CW complex very explicitly in the affine case. Some of the proof of this step relies on the construction by McCammon and Salway, which I hinted at, and they complete the poset to a lattice. They add elements to make it a lattice. So through that construction, we can safely say that we use this idea of completing to a lattice. It's not clear if this is feasible in general, because you don't just complete to a lattice. You need to do it in a way that makes things work.
Other questions? Would you make a little comment on why the k-pi1 conjecture implied the torsion freeness?
Oh yes, torsion freeness is easy because you have a k-pi1 which has the homotopy type of a finite dimensional CW complex, and so the homology only lives up to a finite dimension. And so if this is a k-pi1, the group cannot have any torsion because a torsion would require homology in infinitely many dimensions.
But then you didn't mention that in your new progress for the, because it's obvious. So there your 24 results.
This one? No, I guess I didn't mention it. Well, I should have said that some of these things were already known in the rank 3 case, including torsion free. Yeah. So the most important thing here for me is that the approach is working, even though many of these consequences were actually known.
Any other question? So if not, let's thank Giovanni again.